We are ready to start chapter 7. We're lumping 7 and 8 together. And we'll have a test then again when we get after chapter 8. Okay, before we get into that, I want to talk a little bit about the Sally Clark case. We talk a lot about misleading statistics here. This is a classic case where statistics were used incorrectly and someone ended up in jail because of their misuse of statistics. Sally Clark had 2 of her children die of SIDS, sudden infant death syndrome, or as in Great Britain they call it cot death or crib death. She was convicted of having actually killed her children because she lost 2 of them to sudden infant death syndrome. And her case was later appealed and she was gotten out of jail, but the damage was done. The family lost everything, including their 2 children, obviously. It was a very, very sad situation. Now, I want to show you a video that deals with this. You can hear it quite well. If you don't see it quite clearly because of the way I'm recording here, you can actually go to YouTube and Google Sally Clark video and this will pop up. It's not a very professionally made video. It's got some spelling errors and it's rather an amateur production in cases, but it does explain what's going on. So let's take a look at the video.
In 1999, Sally Clark, a lawyer, a wife, a mother of 2, was convicted of murdering her 2 baby boys. Christopher, who was 11 weeks when he died, and Harry, who was 8 weeks old when he died. Although baby Christopher's death was reported as a lung infection by the examiner, after the second baby, Harry, died, it was changed to suffocation. Mrs. Clark was sentenced to life in prison because the UK does not have the death penalty. She appealed her case after a year because the prosecution was very suspicious, but she lost. He was released after 3 years of serving the sentence because the prosecution's case continued to get holes in it. And she was found innocent and let go. But this could have all been avoided if the experts had just understood some simple statistical mathematics. They made an error, and Sally's family suffered, and Sally suffered the most. With flaky evidence and not a good case in the first place, how did the prosecution achieve the conviction of Sally Clark, a woman who had already suffered beyond the imagination by losing 2 infants, all of her children? Her defense bankrupted her family and her husband. They had to sell the family home in England. How could this have happened? The answer? Misuse of statistics. Sir Roy Meadows, expert witness for the prosecution and a pediatric expert, testified that the odds of one family losing 2 babies to cot death, or in other words, unexplained baby death, was 1 in 73 million. Let's see how Mr. Meadows came up with this figure. The odds of cot death in England, according to an actual statistic, is actually 1 in 1,300. So 1 in 1,300 families suffers an infant death for no apparent reason. However, the good Mr. Meadows modified the probability to 1 in 8,500 because the Clarks were financially well off and did not smoke. To calculate the probability of 2 independent events, such as 2 babies dying in the same family, is the probability of one event times the probability of the next event. And that's the probability that both things can happen. So here's the first problem in the calculation. of 1 over 8,500 times 1 over 8,500 does equal 1 over 73 million. But the actual odds of having one cot death is 1 in 1,300. But the odds of having a second, if you'd had one, is 1 out of 100, which means that people that have had one cot death are prone to having a second one. This is called conditional probability. Not well understood by a lot of people, including doctors and experts. Conditional probability means the fact that one thing has happened means that another thing is more likely or less likely to happen now. For example, what is the probability or the likelihood, same thing, that you will slip and fall today on the sidewalk? If you're not an accident-prone person like some people you might know, then the probability is very low. Now, what about if it's been snowing and the snow on the ground freezes and turns to ice? The probability of slipping now goes up. And so the probability of slipping changed because of something else that's happened, namely the snow and the ice. So when the probability of one event is dependent on another event, we call this conditional probability. The events are not really independent because one affects the other.
Sally Clark's case was viewed as a non-conditional probability problem, where the chances of a first and second cot death were calculated as 2 first cot deaths.
To accurately calculate the probability of 2 infants dying in the same family of cot death, you would have to use this formula. 1 over 1,300 times 1 over 100, which is 1 over 130,000. That translates to about 5 families per year to have cot deaths, not 1 every 100 years. Quite a difference. Although this is still pretty rare, it's a long way from 1 over 73 million. That's like winning the lottery. You might consider that, but even these odds, someone does always win. It happens, doesn't it? So the jury and the media became focused on that 1 over 7,300 million figure, even though it was completely wrong. People tend to believe experts, even non-experts, when they use statistics, because most of us don't understand the numbers well enough to question them. After the statistical group in UK challenged the misuse of statistics in the courtroom, many other women were released from prison, perhaps reducing their heartbreak, but of course never removing it. Sally Clark endured the most heartbreak of any person could ever have, and that is the loss of her children. But Sally lost 2 and then was in prison because of the misuse of statistics and probability, and the belief that experts know more than we do. Because the public does not like to learn about statistics and relies on experts to tell us how things are, and because many experts do not really understand statistics and probability, tragedies will continue to happen. The only way to stop these kind of tragedies is to become educated in statistical methods and probability ourselves. Learn to think for yourself. The experts are not who you think they are or who they want you to think they are. Learn the statistic methods in your class. Know the material well. You'll probably find your professor making mistakes. Everybody does, but very few are caught. Anyway, have fun, learn statistics and probability, and don't forget Sally Clark in your prayers.
Okay, as he mentioned, they simply multiplied the probability of having a SIDS death times itself for 2 kids. And they are not independent events. It's like saying the probability of getting hit by lightning is 1 out of 8,000. What's the probability of get hitting twice? You can't say it's 1 out of 8,000 times 1 out of 8,000. Maybe you're someone who likes to play golf in the middle of a thunderstorm and is holding a club above their head. I mean, it depends on what you're doing. And they have found statistically, genetically, there are health reasons why a family suffers a SIDS death, and it's more likely they will have a second. So it was a very tragic case, but using statistics incorrectly with events that were not independent. All right, today we're going to start chapter 7, and we're going to talk about using samples rather than single elements. Like, for instance, when you were doing the Shy Sam problem and saying, what's the probability that a girl's height is taller than Sam's? And we found Z values and did all kinds of things. But wouldn't it have made more sense to use larger samples than just one person? For instance, down here, if you're doing a test to see if a factory is truly producing items that weigh 500 grams, which makes more sense, to just arbitrarily pick one item and see if it weighs 500 grams, or if you would pick 10 items and see if the mean or the average of all 10 would be at 500. I would think the second way is much, much fairer. And instead of 10, suppose you use 15, 20, or 30 items in your sample. Wouldn't that be an even more of a fair way to calculate whether they're actually producing items that average at 500 grams? So sample size is huge, and that's today what we're going to zero in on. Suppose you have a group of 5 men. Here's their heights. Let's find the population mean of their heights. So I'm going to take 76 plus 78 plus 79 plus 81 plus 86 and divide by 5, and I get 80. The population mean for their heights is 80. So mu is equal to 80. Okay, now I've taken all samples of size 3. Okay, samples of size 3, 3 men, and I found the mean of each sample of size 3. Okay, let's make a dot plot. So I'm going from roughly 77 to 82. So I'll start at 77, 78, 79, 80, 81, 82. Let's put dots. 77.67, 78.3, 80, 79.67, 78.67, 81, 79.3, 81, 81.67, and 82. Okay? All right. Determine how many averages actually equals the 80. There's only 1 out of 10 that actually equals the 80. How many of the averages are within an inch, equal or less than an inch? So how many of the averages, here's the mu is 80, if you go 1 inch above and 1 inch below, do you see that there's 5 of them, 5 out of 10? We have a 50% chance of being within an inch of the mean, right? By using samples of size 3, okay? Now, what if instead of using samples of size 3, what if I use samples of size 4? Okay, so samples of size 4, if you do a 5C4, you can figure out how many samples you should get. 5C4, I think, is 5. Let's see if I can get all 5. I'm going to have 76, 78, 79, 81. There's 1 sample of size 4. How about 76, 78, 81, and 86? 76, 79, 81, and 86. I need 2 more. 76, 78, 81, 86. How about 78, 79, 81, and 86? There's 4. I need 1 more, darn it. 76, 70, here, 70, nope, did that one. 79, 81, and 86. Now, what's the last one? 76, 79, 81, and 86. 76, 79, 81, 86, 76, 78, 81, 86, 76, 78, 79, and 86. There it is. 76, 78, 79, and 86. Okay? I think I have them all now. Okay? Okay. Well, let's find the means for samples of size 4. It's going to take me a second here. I'm going to have to add these up and divide by 4, so stick with me. So I've got 76 plus 78 plus 79 plus 81 equals divided by 4 equals 78.5. Okay. Divided by 4 equals 80.25. I'm double check that first one and make sure I did it right. Yep. Okay, how about the next one? 76 plus 79 plus 81 plus 86 equals divided by 4 is 80.5. Next one, 78 plus 79 plus 81 plus 86 equals divided by 4 is 81. And the last one, 76 plus 78 plus 79 plus 86 equals divided by 4 is 79.8. Okay, on the dot plot, I use stars. This is when n is equal to 4. Notice this was when there were 3 in the sample. This is when 4 is in the sample. This one should be more accurate. 78.5 here, 80.25 here, 80.5, 81, and 79.8. Okay? Wow. Going from the points to the stars, look how the stars more closely group around the population mean of 80. Back in the dots, we had 50% of them were plus or minus an inch. How about we look at the stars? How many there are plus or minus an inch? And we have 4 out of 5. We have 4 out of 5. This one is not, but this one is, this one is, this one, and this one. They're all within plus or minus an inch of 80. So that's 4 out of 5 or 80%. If you use sample size 4. If you increase the sample size, it increases the accuracy. Okay, what if we went to samples of size 5? There's only one group of samples of size 5, and the sample mean is the same as the population, and that would be 100% of them are within plus or minus 1 inch. Okay? There's a great picture on page 302, or pardon me, page 300 in your textbook. If you look on page 300, look at the bottom of the page. It shows this is the same problem we were working on. It shows samples of size 1, samples of size 2, size 3, size 4, size 5, right? Much, much, much clearer picture as to how it gets much more accurate as you increase the sample size and you're more closely clustered around the population mean. Folks, the dirty little secret is it's almost impossible to find a population mean. We are desperately hunting ways of approximating the population mean because who wants to add up everybody in the United States and what their favorite pie is? Are you with me? If we can do it with samples with a certain amount of accuracy, it's a much better way of doing it. We want to do page 302, problem 7.8. 7.8 on page 302 is very similar to what we were just doing, okay? I've got in 7.8, I've got data 2, 3, 5, 7, and 8. And I want to do the same kind of thing we just did. First, let's find the population mean. Mu Add these up, 15 and 5 is 20, 25 divided by 5. The population mean is 5, okay? So let's start with n is equal to 1, right? We'll start with 1 for the sample size. We'll then go to 2, 3, 4, and 5. And we want to see if we can get the same effect as on page 300, getting more accurate with an inverted pyramid. Now, when n is equal to 1, okay? When n is equal to 1, here's 2, 3, 4, 5, 6, 7, and 8. When n is equal to 1, samples of size 1, we have groups of 2, 3, 5, 7, and 8. There's one item in each group. So how do you find the mean of just one item? You have the number 2, you divide by 1, it's still 2. Okay, so when n is equal to 1, when n is equal to 1, I get a dot on 2, 3, 5, 7, and 8. And the problem in the directions ask you to calculate what is the probability of finding that it's going to equal the population mean. Did we have any that equaled the population mean? We had 1 out of 5. Okay, so equaling the population mean is 1 out of 5, or 20%. What's the probability that we're plus or minus a half of an inch, or a half on either side? A half on either side, there's only one of them, and that is 20%. Okay? All right, let's go on now to n equals 2. When n is equal to 2, if you do a 5C2, you get 10 items. Okay, so let's see if we can get 10 here. 2, 3, 2, 5, 2, 7, 2, 8, 3, 5, 3, 7, 3, 8. 2, 3, 2, 5, 2, 7, 2, 8, 3, 5, 3, 7, 3, 8. How about 5, 7, 5, 8, and 7, 8. Okay? Now I want to find the means. So the means here would be for 2 and 3, I'm going to add up and divide by 2. So 5 divided by 2 is 2.5. 2.5 is here. Okay, I'll do a star. 2 and 5 is 7, that's 3.5 when I divide by 2. 2 and 7 is 9, that's 4.5 when I divide by 2. 2 and 8 is 5. 2 and 8 is 10, divided by 2 is 5. 3 and 5 is 8, divided by 2 is back to 4. Okay. 3 and 7 is 10, that's another 5. 3 and 8 is 11, that's 5.5. That's 6. 6.5 and 7.5. What's the probability of hitting the mean? I have 2 out of, I hit the mean twice. 2 out of 10 is 20%, just like this one. But now, what's the probability of being within a half on either side? 1, 2, 3, 4 out of 10 is 40%. Okay? Well, let's go on. This is when n was equal to 2. Let's now go to n equals 3. See if I can get, I think a 5C3 is 10 also. See if I can get 10 out of this. So I'm going to try. It's going to be 2, 3, 5, 2, 3, 7, 2, 3, 8. Okay. 2, 3. I think I did all the 2 3s. How about 2, 5, 7, 2, 5, 8. Okay. I did all the 2 5s. How about 2, 7, 8? Okay. How about with some 3s now? 3, 5, 7, 3, 5, 8. 3, 7, 8, and 5, 7, 8. I think that's all 10. Okay, now let's see if we can find averages for groups of size 3, and I'll put dots here once again. So you add up and divide by 3. So we have 10 divided by 3 is 3.3, which is right about there. 12 divided by 3 is 4. Okay. 13 divided by 3 is 4.3. Okay. 7 and 7 is 14 divided by 3 is 4.7. There's our first one that's within half. Okay. 7 and 8 is 15 divided by 3 is 5. So we got one there in that range. 17 divided by 3 is 5.7 over here. Okay. This is 15 divided by 3 is 5 again. Okay. 1, 2, 3, 4, 5, 6, 7. And here is 8 and 8, 16 is divided by 3 is 5.3 here. Okay. And I have 2 more. So 18 divided by 3 is 6. And 20 divided by 3 is 6.7. What's the probability of hitting the population mean? Just like the last one, it's still 20%. What's the probability of being within a half? This one, this one, this one, and this one. And it's the same as the last one. But we have increased our accuracy because look at all the dots. Even though these are the same as the last one, we've increased our accuracy because these are more tightly clustered around the population mean. Let's go to groups of size 4. When n is equal to 4, see if I can get all 4. So we have 2, 3, 5, 7, 2, 3, 5, 8, 2, 3, 7, 8, 3, 5, 7, 8. I need one more. 2, 3, 7, 8. I need a 2. 2, 2, 5, 7, 8. All right, so I need to add these up and divide by 4. So I have 17 divided by 4 is 4.3. I have 18 divided by 4 is 4.5. I have 20 divided by 4 is 5. I have 23 divided by 4 is 5.8. And 7 and 7, 14. 22 divided by 4 is 5.5. Did I do those correctly? 17 divided by 4 is 4.3. 18 is 4.5. 20 divided by 4 is 5. 23 divided by 4, yep, 5.8. And 7 and 7, 14, 8 is 5.5. Okay, let's do these with stars. So I've got 4.3, okay, which is here. 4.5 is within the half. So there's one of those, 5. Okay, 5.8 is here, over here, out of the range, and 5.5 is within the half. So first, what's the probability of hitting? Man, it's 20% again. Isn't that weird? Okay. What's the probability of being within a half? 1, 2, 3 out of 5. That's 60%. Okay? 60%. And we have increased our accuracy with the percentage. It's more clustered. If we go to 5, there's only one group and it has a mean of 5. So that is 100% and 100%. Okay? You need to be able to make inverted pyramids like this to demonstrate that you understand as you increase sample size, you get closer and closer to the population mean, and it's much more accurate. Homework, there's a couple extra problems and some problems in the book.